Hello, good morning, my dear students. Today we're going to learn about advanced mathematics in its introductory stage. So, I'm an introductory stage for you because this is your first time to do it. Right, so advanced mathematics for mechanical engineering. So as you can see in here, we've got numerical techniques, we've got finding roots of equations, curve fitting, interpolation, and so on, up to differential equations. But of course, we will not be taking up differential equations in total. So whatever will be those that we cannot take up in differential equations, maybe we can put it here. And here are the topics for prelims, those that were ticked in red. Okay, red. So you have numerical methods, the Taylor series, matrices, operations, vectors, and determinants. We have linear systems of equations, roots of equations. So those are the ones that we're going to do. But for now, of course, we have to start from the introduction. And this is the numerical methods introduction. From those that I have highlighted here, numerical methods are mathematical techniques that can sort out two complex solutions, time-consuming solutions, or those that are impossible to solve analytically. But of course, here in our advanced mathematics, we will still be guided, and it will be using some theories that we can apply in solving some mathematical problems. What is the importance of numerical methods? So numerical methods play a crucial role, an important role in various scientific and engineering fields where analytical solutions are often difficult to find. Let's see. Okay, but as I've said, we will not be settling to those questions where we will just be getting the solution from our mind, right? We still be guided with some theories or some formula. In numerical methods, sorry for the background, there are some disturbances. One of the application is discrete algebra. And to differentiate discrete with continuous, then from the word discrete, these are finite numbers. These are those that have a start and an end. And the opposite of finite is infinite or infinite or, it's infinite. There's no end, isn't it? Like a negative infinity and a positive infinity. There's no end for the negative number. And for positive, of course, you do not know when to end. But if you say finite, we have 1 to whatever, 1 to n, 1 to 100. But if you say negative infinity to positive infinity, all those numbers that you can think of, and there's no end. You cannot get differences because there will always be remnants between numbers. All right. And also, when we talk about numbers, continuous, infinite, finite, then we are talking about real numbers, as I have mentioned a while ago. And a definition of what real numbers are, they are presented in a Venn diagram. So for real numbers, as you can see, we've got the natural numbers, the integers. If you say integers, these are whole numbers. And natural numbers from 1 until whatever number you can think of now. And whole numbers will be those without decimal places, or this could be radicals, but you can extract their value and the answer or the result will still be a whole number. And integers could also range from negative finite number in the negative side, or if you are thinking of a number line now, then a number line would be, this is the zero and this is the negative values of x's, and you have the positive values of x's. And of course, below the T lines, or the cross-section lines, this will be negative y, and this will be positive y, where positive y, negative y, or all numbers in this Cartesian coordinate system are all finite numbers. You can also put some decimals, but still a decimal with an end, like 2.5, but they are not continuous. All right. And also, there are rational numbers, as you can see here, where they are continuous decimal, but we can make them, but they could be possibly converted to a rational number. So rational numbers, apart from the whole numbers, or like the radicals that you can extract the square root, the cube, or whatnot, you can also have a fraction, you can also have a decimal, a negative or a positive, and repeated decimal places. These are still rational because there is an end to it. There is an end number or a last number. Now, another kind of real number would be the irrational number. Of course, if we have the irrational, we have the rational numbers. We have learned about the use of pi, and we have been putting it in our equations, in statics, and in analytic geometry, or whatever branch of engineering math subjects we had in the past. And pi is actually 3.1416 blah 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 blah, a lot of numbers. It's infinite. Or the square root of 10, for example. Let me just pull out my calculator here, and let's just try to put the pi value. I hope I have it here. Oh, no, I don't have. So let's just do the square root of 10. Square root. Look at that. The square root of 10 gives you 3.16 and a lot of numbers after that. So we do not know when this decimal place ends. In this case, if you have non-repeated decimal places, then you call them irrational. Or for example, the 2 square root, again, it's 1.414 and the decimal number doesn't end. Or 3 square root, again, it's 1.73 and the decimal numbers doesn't end. In which case, then you will say irrational numbers are numbers with decimal places that has no end. It keeps going on and on and on and on forever. So I have here an activity that we can do. Rational number is a ratio that is now the definition of a rational number is it's a ratio of 2 integers. So if it's a ratio of 2 integers, a natural number can be a ratio. If there is a whole number 5, this could be a ratio by putting a by putting a denominator, which is 1. A whole number has always a denominator equal to 1. Even just a variable x, it has a denominator y. Even an x square, it has a denominator of 1, I should say, right? Even a negative number. So these are ratios of 2 integers, like 2/3. 2 is an integer, 3 is an integer. So a ratio of that gives you a rational number. All right, so I've got some squares here or rectangles here with rational numbers inside, and we're going to classify them. Okay, I hope this works today. All right, there you go. It works. 3/4 is 0.75. So 0.75 means a finite number. And so we have to put that in the rational number box, isn't it? And 0 is a rational number. Okay, because it is included in the Cartesian coordinate system. It's in the number line, so 0 is rational. Um, the repeated decimal is also a rational number. Why? Because we can make this a rational later with it can be converted into fraction where the numerator and denominator will be finite numbers, and that's what we're going to do later. A negative number is also a rational number. The square root of 7. Let me just put it here in my calculator. Sorry for that. Okay, I'm not a walking calculator. I have to be very honest with that, and no one is, except maybe those who are really into this square roots and cube roots. So we still need the help of a calculator. So we have 7 square root. Look at that. All the decimal numbers are unending, isn't it? So after 91 in here, as you can see at the last numbers, then at the last positions, these numbers can continue. If you have like 1,000 digit calculator, then all those 1,000 numbers will show. So we can put this 7 here in the, we can put the square root of 7, I should say. Sorry for that. Oh my God, please don't shame me. It's just as though, because I am live at the moment. Right, so the square root of 7 will be in the rational number. And how about 7 over 6? 7 divided by 6. Even if you do not know the quotient, for as long as the 7 and 6 are a ratio of two integers, then I would say this would be a rational. Why? Because the definition of rational is both the numerator and the denominator are integers, and 7 is an integer, and negative 7 is an integer, because you can see this number in the number line. And of course, 0.25 is a decimal number, but it just stopped from 0.25. There are no other numbers after 5. Then you call that irrational. Sorry for that. Rational number, because you can convert it to a ratio of two integers. And we only have 10 left in here. Sorry for that. And we have to put it. Why is it that I only have one irrational? Because you can anyway play around with the number, whether it will. It's not playing around, but you can check it with a calculator whether it gives you an ending decimal or not. Okay, so let's take this 0.77 in here. Let's take this one. Converting a repeated decimal into a rational, a ratio of two rational numbers. So how can we convert? You have to listen here very carefully, because I will be giving you something to do at the end of my explanation. So how are you going to convert a repeated decimal to a fraction? So I already took a solution from the internet, and so it will be very quick. So I have here for example, a repeated 0.77. Okay, this is the one that I have put in the activity. Then I will call this one a 0.7 repeated. Let x be equal to 0.7, and you put a bar on top. It means this will be 0.7777 forever. All right. Now, hang on. I'll just rub it off so it will be a cleaner presentation. And then you have to do 10 minus x. All right. Why is it 10 minus x? Because this is in the 10th place. So you do 10 minus x will be, oh, sorry. What am I saying? I'm sorry for that. I'm just overwhelmed. 10 times x. So if you have 0.777 repeated and you're going to multiply it by 10, then you just have to move the decimal one step backwards. So you will have 7.7 repeated decimals. It means, again, this will be 7.7777 forever. Okay, so that's the first step. The second step, Right. What's the first step again? You have to present x equal to the repeated values, which is x is equal to 0.7 repeated. And then 10 times x, after 10 times x, you just have to move the decimal one step backwards and you will have 7.7 repeated. In that case, you will have this one. And of course, above will be this 7.77. Then you get the difference. That's the difference. Let me just write the first step. The first step will be this. The second step will be that. And the third step is to get the difference. 10x minus x. So you put your 10x here, which is 7.7 repeated, minus 0.7 repeated. And you have to define it here. What is 7 repeated? 7 repeated is 7.777. Then you put a dot. It means that there's still 7 after the last 7 that you have written. And then minus 0.77. Then you get a 7 difference. All right. And you can also get 7 a difference here. This is just a presentation, detailed presentation, but you can cut that off. Actually, you can cut this off. You can cut this point in here. Let me just put a black one. You can cut this off and you can just consider this bit. Okay, you can just consider this bit. It will still be the same. Let's make it cleaner. All right, so the fourth thing you're going to do is to take the difference, and that is 10 minus x will be 9x. 7.7 repeated minus 0.7 repeated will be 7 only. Correct? It will be 7 only. So let me just do it again. 10 times, or 10x minus x is equal to 7.7 repeated minus 0.7 repeated. So this will be 10x minus x is 9x equal to 7.7 repeated. This will go, and you will only have 7 in the other side of the equation. So in that case, then you can do, if you solve for x, that will be 7 over 9. There you go. You have made a 0.7 repeated to a decimal of 7 over, to a fraction, which is 7 over 9. Okay, let's solve the other one. For example, you have 1.222 and 2 is the one repeated here. So you can just write 1.2 and then 2 above. Okay, so 10x will be, right, 1.222 times 10 is just moving the decimal place 1 to the right. So 1.222 goes there. You have 12.2 repeated. Again, if I have 1.333 times 10, then you have 13.3 repeated. Move the decimal 1 place to the right. All right. So what's next? Get the difference. This is the first step. The second step is the 10 times x, and then you get the difference of the two. So 10 times x is 12.2 repeated. You have x is 1.2 repeated. Then you will have 12 minus 1. I'll put it here. 12.2 repeated minus x is equal to 1.2 repeated. The difference will be, this will go, and 12 minus 1 will be 11. 10x minus x, that will be 9x. So the answer will be, you have to divide both by 9, then x will be 11.9, and that, oh, why 11.9? I'm sorry. 11 over 9, and that's the answer for your value of x. Okay, so which is the same as this one here. Okay, so in this case, you now have your homework. So your homework, my dear students, let me just remove this up there so you cannot see that. This will be your homework. Give at least 5 examples of rational and 5 examples of irrational, and give 3 examples of repeated decimals converted to fractions where both the numerators and denominators are integers. Yes, you have to do yours. Okay, I will not give my value, you have to give your values. So this is your first homework. So this will be homework number 1. Where will you write them? Write them in your notebook, and I will mark them when we meet. Okay, to be marked on Saturday. Thank you so much. Okay, that's 1. So homework has already been given. Next topic is about discrete mathematics topics. We have set theory. We have set theory. We have graph theory. We have logic. We have permutation. We have combination. We have sequence. We have series. So these are the ones that we're going to do in the next videos. But of course, I cannot cover everything. I will do the combination, the permutation and combination for this video. I will start with this together with the combination, and then the set theory will be done next. Okay, so there will be 2 videos that I will be sending today. All right, so let's start with permutation. What is permutation? Permutation is the different arrangements that can be made with a given number of sets, taking some of or all of them in a particular sequence at a time, are called permutation. All right. And of course, the combination of those is in the theory of combinatorics. So, yeah, the permutation and combination always come together. Right, so let's do the discrete mathematics examples on permutation and combination. You have to listen here very carefully. The first example about combination would be determine that in how many ways can 3 prizes be shared among 4 boys. So I have here an illustration. In how many ways can these 3 prizes be shared among 4 boys? Now, there are conditions here. Number 1 condition is no one gets more than 1 prize. So if 1 prize has already been given to 1 boy, then this boy will not receive anything anymore. The 2 prizes will be distributed to the 3. And when these 2 will be given to the second boy, for example, or any of the 3. By the way, this one is not always the first boy, okay? I just have chosen it for a presentation, orderly presentation. But it can be the second boy, the third boy, or the fourth boy who can receive the first prize. The second prize could either be the second, the third, or the fourth, right? So the second prize for orderly presentation, then I would say, okay, I will let the second boy receive it. After that, there's only 1 prize that is left, and that's prize 3, which can be received either the third boy or the fourth boy. So whoever receives it, then that would be the third person, isn't it? So again, for purpose of orderliness, let me pick the third one. Okay. In which case, if we're going to write the total number of ways, then it will be 4 times 3 times 2. So there are 24 ways to share the 3 prizes amongst 4. How is this? Because it says here, how many ways can 3 prizes be shared to four boys? So the 4 boys can get any of the 3 prizes. If one boy has received already 1 prize, there are 3 boys left to have one of the 2s, because there are 2 prizes left. And there are 3 boys left to receive. Next is when the second boy receives the second prize, there are 2 boys. So the 4, 3, 2 are boys to share. 4 boys to share the 3, 3 boys to share the 2, and 2 boys to share 1. So 4, 3, 2 is equal to 24. That is when no one gets more than 1 prize. But there's another condition where it says a boy can get any number of prizes. In that case, the first, any number of prizes, it means that prize 1 can be given to any boy, and there are 4 boys. So the first boy can take it, the second boy can take it, the third boy can take it, the fourth boy can take it. So 4 ways to share prize 1 without restriction. P2, 4 boys can share as well. P3, 4 boys can share as well. So without restriction means that one boy can have the 3 prizes, isn't it? Each one boy can have the 3 prizes. It means there's no restriction at all. So to do that, there are 4 ways by which the first prize can be given. There are 4 ways as well, or there are 4 recipients. There are 4 boys who can receive. And that's for the second. And for the third, there are 4 boys who can receive the third one. In that case, you have 4 cubed, so 64 ways to receive the 3 prizes amongst 4 boys. I hope that is clear. Now let's go to another one, another example. Suppose you have a set of 4 different books and you want to arrange them on a shelf in a specific order. What does it mean? I numbered the books 4, 3, 2, 1. I can put 4 here, I can put 2 here, I can put 3 here, and I can put 1 here. Correct? Or I can put 4 here, I can put 3 here, I can put 2 here, or I can put 1 here. So there are a lot of combinations that you can do. How are you going to get the total combinations? Or there are a lot of ways. So you do, if this book goes to the first position and the third book or number 3 book can also go to the first, and the book mark 2 can also go to the first, and book 1 mark 1 can also go to the first. It means that 4 books can occupy the first position. And then for the second position, if this 4 here will be canceled already, or it has already been positioned, then there are just 3 books left to position in number 2. So there are 3 books to be positioned in number 2, and there will be, so if this will be removed, there will be 2 books to be positioned in 3. Or third space, it means, if there are only 3 spaces, okay, for the 4 books. That's it. So how are we going to compute it? 4 times 3 times 2, that will still be 24, like what we did in the prizes previously. And then each book can be placed in any of the three, in any of the three. So the first book can be the first, the second, or the first one can be in the first position. Can the four the four books can be in the second, the four books can be in the third. So you will do 4 times 4 times 4. Four books can be in the first one, in the first slot. Four books can be in the second slot, and four books can be in the third slot as well. So you have 4 cubed, 4 times 4 times 4. 4 times 4 is 16. 16 times 4 gives you 64. So there are 64 ways to position the books in those slots given. And another one. Okay. About the card. You have a deck of 5 playing cards. So you have ace, and then you have, sorry for that. You have the ace card. You have number 1. You have number 2. You have number 3. You have number 4. And you have number 5. So you have this deck of different playing cards. The question is, you want to draw 3 cards. What does it mean? You want to take 3 cards from the deck. So example, you want to take 2, you want to take 3, and you want to take 1, for example. Oh. Okay. Without replacement. But okay, so let's do this one. You want to draw 3 cards from the deck without replacement, meaning once a card is drawn, it's not put back into the deck. And we know that, for example, we know that if we're going to draw, for example, a card in here, then we have to put them back together, isn't it? If I took the middle one, then you put this card back. You're going to put this card, sorry for that, there. So you only have 4 cards left, and you draw another, for example, draw another. So you have to put this one here again, isn't it? So they will always be a deck of cards. All right. In how many ways, it says here, in how many ways can you draw the cards? If, number 1, the first card can be any of the 5, the second can be any of the 4, and the third card can be any of the 3. So you do 5 times 4 times 3. So you can get or pick a card out of the 5, and then you can pick the second one out of the 4. You can pick the third one out of the 3. So in that way, you have 60 ways to do it. Next one. It says here, each card can be drawn in any order without any restriction. So what does it mean? Without any restriction, there are just 5 cards each time. You pick one and then put it back. So again, it goes back to 5 cards. You pick another for the second one, and then you put it back. In that case, there will always be 5 ways. You pick one card. You pick one card from the 5, then you have the first card. And then You pick one card from the 5, then you have one card pick. You put it back. So the second card will be picked from the 5 again, and that will be your second card. And then put it back. You have the third card from 5 cards again. In that way, you will have 5 times 5 times 5, and you will have 125 ways to pick the 3 cards when you are putting it back after picking it. All right. All right. You can read the last one. And I just want to explain about the sum of 4 digits formed by using, okay, in how many ways can we do it? All right. Find the sum of all 4-digit numbers formed by using 2369 in which no digit is repeated. So what does it mean? I've got 4 numbers, and we are going to arrange them in such a way that there will be no digit repeated in our number holder. So we have a number holder here where we have the units place, you have the tens, you have the hundreds, and you have the thousands. Okay? In numbers, we do units. Hang on. In numbers, we have units, we have tens, we have hundreds, and we have thousands. Okay? So, if 2, it says here, if 2 occupies the units place, then you have 369 to occupy either the tens place. Correct? And when 3 goes to the tens place, then you have 2 numbers in the hundreds place. And if 1 goes to the hundreds place, then you only have 1 value, 9, in the thousands place. Right? To do this, there is a formula. This is the one that I was telling you a while ago, that not all those that we're going to sort out will be coming from our mind. There will always be a pattern, or there will always be a theory or a formula that we can use. In this case, we have how many combinations, by the way? It says here we have to form 4-digit numbers, different 4-digit numbers, yeah? We're going to form the sum of all 4-digit numbers wherein no digit is repeated. We're going to have those sums. Okay. So there is a formula we're going to use, and I'll do it shortcut. There are 4 digits altogether, so we will use a 3 factorial because one number will be occupied by any of the 4 already. So you only have 3 remaining. So you do 3 if there are 4 numbers. 4 minus 1, you start with 3 factorial. So 3 factorial times 1, 1, 1, 1. What does it mean? 1 for the digits times 1 times 10 times 100 times 1,000. Are we okay with that? Okay. So, sorry for the background because my husband just arrived and his car is big one, so you can hear the annoying sound. Okay, so times, so these are the positions, place values, I would say, or place values. And you put the digits you want to add. So 2 plus 3 plus 6 plus 9. And the factorial will do the rest for you. Okay? So it's not necessary that this will be the first digit, not necessarily this is the second, not necessarily the third, not necessarily the fourth. You just have to bang whatever number you want to get the combination, and the computer will do 2369 as one, 396 as another, or 2639, or 2396, or 2936, and so on. And in that way, you will have a combination of 133,320. 133,320. Okay, sorry for the disturbance. All right. So for your homework, it will be find the sum. This is homework number 2. This will be your homework number 2. Oh, I'll use this one. Sorry. There. So this is homework 2. Okay. There. So you have homework 1 and homework 2. All right, I'm going to end from here and wait for my next video that is about set theory. All right then. Happy weekend, and do your homework 1, homework 2. Within the day, set theory will be given. Bye for now.